I'll record this so that people watching the video can do it. Okay, so there's 2 weeks of class left and then finals week, right? So kind of just to give ourselves like a little, what the rest of the semester is going to look like here. And I guess I had the red pen on. So that's okay. So our class meets right on Tuesdays and Thursdays. So today we are going to, do sections. We're going to do section 10.5, 10.1, and depending how 10.5 and 10.1 go, 10.1 is like in 2 parts. So I don't know how far we'll get. We'll get through all of part 1 in terms of the homework, but we definitely won't get through all of part 2. And then on Thursday, we will finish 10.1. And I guess I probably should put the dates. So today is the 27th. Thursday, the 29th, we're going to finish 10.1, and then the last section of stuff we have to do is 10.3. So we're doing it in a little bit odd order, but that's it. So this week is the end of me lecturing about stuff for the for our class. I did put up the review sheet for the final, and so at the end of class, I might pull that up. So next Tuesday, which next Tuesday is the 4th, so on the 4th, we will actually review for the final. So between now and next Tuesday, you probably want to look at the review sheet I put up, so you can ask me questions about the final and stuff like that. Next Thursday, which is the 6th, I will not be here, but Brian will actually do an SI session during class time. So, Brian, SI session during class. And then the following Tuesday, which is the 11th, that is our final. So, we're coming up on the end, right? There's not a ton more to learn. There's the stuff we're going to learn this week from chapter 10 is stuff that's important if you're going to go on and take Calc 3. I should say some of the stuff is important if you have to go on and take Calc 3. Some of the stuff is just kind of interesting stuff. So, but that's kind of the plan for the rest of the semester. Does anybody have any questions? So the final is, it's cumulative, but it's, it won't be as intense. And I'll pull up the, so some of section 10 will be on the final exam. Yeah. And I'll pull up the review sheet and we can go over that, either at the end of class. I'll probably actually wait and pull up the review sheet at the end of next class, since we will have gone over everything, so that then what is on what. But the review sheet is up there, if you don't want to wait till I go over it next class. Other questions? Okay. No, I actually don't think section 10 is that hard. And depending, some of section 10 is stuff that you might, like you theoretically saw in math 1. You at least saw, some of it in math 127. So some of it actually should just be review. So section 10.5 is what's called parametrization of plane curves. Okay, so the idea with parametrization, and so parametrization is something you do a lot in Calc 3, is that sometimes it is easier to write an equation. It's easier to do some of the math that we have to do on an equation or a function if we deal with it in terms of a third variable. So you might not think that introducing another variable into a problem might make it easier, but in terms of derivatives and stuff like that, in Calc 3 it actually does. And, derivatives you could kind of hit or miss, but integrals for sure. When you're integrating things in Calc 3, being able to parameterize stuff is really important. So sometimes it is more convenient to write equations in terms of a third variable. All right, so let's think about a reason, like an actual, like a physical reason why that might be. Okay, so if you think about it, if I took a ball and I propelled that ball, so I projected that ball up into the air, right? So we, you run up and you kick a ball, right? And it kicks up into the air. The ball would probably make some type of arc like this, right? And the path, right? So here, the path, ball kicked into the air follows can be modeled by y equals minus x squared over 72 plus x. So here's just, I kick a ball, it happens to follow a path that looks like this. And the thing is that x is, in this case, is representing horizontal distance from where you kick the ball, and y is representing vertical distance from where you kick the ball, so how high it's going, right? So y is representing the height of the ball, and x is representing how far away the ball goes. So that's nice, but that doesn't really tell us anything about like how fast the ball goes up in the air and comes back down. So there's nothing here dealing with time. So this is a place where, so this is where calculus and physics begin to intersect, a bunch. So this is a place where being able to know stuff about the time might be helpful, right? So this gives x and y coordinates, but doesn't involve time. But we could rewrite it. So we could write this. We could write y equals minus x squared over 72 plus x as x of t. So x is some function of time, and it's going to be 24 square root of 2t. And y is some function of time, and it's minus 16t squared plus 24 square root of 2t. So the idea here is I can break my equation up, right? My y equals the stuff with x. And now I actually can figure out, well, how far away is the ball at any given time? Or how high is the ball at any given time? So actually adding, in this case, the third variable makes it helpful in terms of practical applications, right? So if you want to know, I kicked the ball, and 2 seconds later, how high is it? Or how far away is it from me? This would give that to you. So that's one of the reasons why parameterization can be helpful. Now, I just plucked all these equations, out of thin air, right? And so the idea is we are going to actually work on trying to figure out what's happening in parameterized problems, right? So a lot of Calc 3 at the beginning, you learn about different ways to parameterize curves. So for us in Calc 2, we're just going to be working with a parameterized curve. So we're not going to be creating the parameterized curves. We're just working with these parameterized curves once they're already given to us. So questions? No. Does anybody need me to wait before I turn the page? No. Okay. All right, so here's the formal definition of a parameter. So just so we kind of have it written down, if x and y are given functions where x is equal to some function of t and y is equal to some other function of t over an interval of t values, then the points x comma y is equal to f of t comma g of t define a parametric curve and t is called the parameter. So the first thing that we're going to do is we're going to work on how do you graph a parametric curve? How do you figure out what's happening on? So to graph a parametric curve, we are going to do the following steps. We're going to try to eliminate the parameter if possible. To get a curve we recognize. And then figure out the direction on the curve. So one of the things about parameterization is generally parameterized things have a direction. So you're going from this t value to this t value. So there is a direction to what is going on. So for example, if we were given this set of equations, x equals t squared minus 4, y is equal to t over 2, and t is going between -2 and 3. So the idea is I want to figure out what does this curve look like, right? So one of the things that I can do is I can try to basically look at my equations and see, is one of the equations, could I solve easily for t in one of the equations? So if you look at my two equations here, could you easily solve for t in one of the equations? Yeah, which one? The x one or the y one? Yeah, so theoretically you could do both, but remember in the x one, if you try to solve for t, when you take the square root, you're going to get a plus part and a minus part. So I don't consider that to be easy, right? That's taking more work because now I have two pieces and I have to put the two pieces together. However, in the second equation, the y one, it's easy to just solve for t, right? Multiply the two up and t is going to be equal to 2y. So from this second equation, we can get that t is equal to 2 times y. So I just multiplied both sides by 2. And then I can plug that back up into the first equation. So if I plug that into the first equation, my first equation was x is equal to t squared minus 4, or x is equal to 2y quantity squared minus 4, or x is equal to 4y squared minus 4. So now I have here, right, an equation where I got rid of the parameter, right? So I was able to eliminate the parameter. Anybody recognize that equation? Could tell me roughly what it kind of looks like. Yeah, it's some kind of parabola. It's a parabola that's on its side, right? Because the y is what's squared. And so if you were to draw that, right, if you were to look at a graph of that, so you would see that it would go sideways like this, okay? So if we were just drawing the curve, like x equals 4y squared minus 4, that's all we would need to do. However, the thing is that we only want the part here that's between -2 and 3. So what I want to do is I want to figure out what are the points, like where's my curve starting and where's my curve ending. So if we look at when when t is equal to -2, and I plug that back into my original equations, x is going to be -2 squared minus 4. So x is going to be 0. And y is going to be -2 over 2, so y is going to be -1. So we're starting at this point here, right? This is the t equals -2 place, right? So when t is equal to -2, x is equal to 0 and y is equal to -1. So this is that point, 0, -1. And then I'm going to do the same thing with where I'm ending. So when I'm ending, t is equal to 3. So x is going to be equal to 3 squared minus 4. So 9 minus 4, which is 5. And y is going to be equal to 3 over 2. Right? So 1.5. So 1, 2, 3, 4, 5. So we're talking about, you know, this point here, which we're going to say is, you know, theoretically this curve keeps, the original curve keeps going. Oops. And we're going to say that is 1.5, right? Because 3/2 is 1.5. So my curve starts at t equals -2, and it goes to here, t equals 3, right? And this is the point 5, 1.5, right? Or 3/2. And so you want to indicate that think of it, when we're doing these parameters curved, we're thinking about them like almost like we're dropping a particle and watching a particle move. So we would have dropped the particle here, watched the particle rotate around this way. So we need to indicate that. So on these parameterized curves, we put some arrows to indicate this is the direction that particle is moving. Questions? No? Okay. Does anybody need me to wait before I go to the next page? No? Okay, so let's do another example. Suppose I have the curve x equals 4 cosine t, y equals 5 sine t, and we know t is going between 0 and 2 pi. Okay, So just like the last one, right? If it's possible, I want to solve for t. So while you could solve for t, the t is trapped inside the cosine or the sine. And if you go to solve for t, you have to get an inverse cosine or an inverse sine, and that's just not super nice. So if you have problems that have a cosine or a sine in them, a lot of times we actually want to use the Pythagorean identity. So remember, the Pythagorean identity says that the sine squared of whatever, in our case we have t, so sine squared of t plus cosine squared of t equals 1, right? So the Pythagorean identity helps us out there. And then each of these equations is easy enough to solve for the cosine of t or the sine of t. So this first equation here, we can get that the cosine of t is actually equal to x over 4. And the second equation, we can get that the sine of t is actually equal to x over 5. So if I plug those in here, we get x over 5 squared plus, oops, not x, right? You guys all let me write x. It's a y. So y over 5 squared plus x over 4 squared equals 1. So yeah, Aiden tried to help me out here and let me know that it was a y. So I've got y squared over 25 plus x squared over 16 equals 1. So does anybody remember from Math 127? I just taught this yesterday to my class. Yeah, that's an ellipse, right? So remember, the number underneath is kind of what tells you this is, remember, 5 squared, this is 4 squared. So in terms of the ellipse, my center here is at 0, 0, and then it's saying go out 5 in the y direction. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 4, 1, 2, 3, 4 in the x direction. And then we're just going to try to make it look kind of like an ellipse. Questions about how I got that?
I actually don't know how to graph that. I was wondering, oh wait, actually no, it makes sense to me. The y with the 5 is on the y-axis and the 4 is on the x-axis because it's under the x.
Yeah. Yeah, and so, like, if you had, if here I had, like, say, like, y minus 1 and, like, x minus 3, then your center would be at 3, 1. So, like, if there was numbers inside here attached to the x or y, that would tell you where our center is. But since there isn't anything being added or subtracted to the x, that's why my center's at 0, and then underneath the y was 5 squared. So I went up 5 and down 5, and underneath the x was 4 squared, so I went to the left 4 and to the right 4.
Thank you.
No problem. Okay, so now the question is, we have to see, just like we did last time, what part of this are we taking, right? So remember, we're going between 0 and 2 pi. So when t is equal to 0, right, x is going to be equal to 4 cosine of 0. The cosine of 0 is just 1, so x is going to be equal to 4, and y is going to be equal to the sine, or 5 sine of t, so 5 sine of 0, which would end up being 0. So when t is equal to 0, we're starting at the point 4, 0. So 4, 0 is right here. So that's where we're going to start. And then we're going to look at the end point, which is t equals 2 pi. So again, we're going to look at x equals 4 cosine of 2 pi, which again is 4, and y is going to be 5 sine of 2 pi, which again is 0. So we end up back at the same point, right? So the problem here is that because we have a circle and I started here and I end back here, I don't know if I went around this way or did we go this way, right? We don't know what direction we went. So we need to pick like a couple more values to try to figure out, are we traveling starting here and going counterclockwise, or are we starting here and going clockwise? So what's another nice value we could try besides stuff between 0 and 2 pi that's nice that we could try? Okay, so we could try pi, yep. So if we look at pi, we'd have x equals 4 cosine of pi. And so that's going to be minus 4, and y equals 4 sine of pi. And that's still going to be 0. Okay, so I know I have a point over here. Part of my problem, though, still is I still don't know, did I go this way or did we go this way to get to that point? So we're going to have to pick one more. Right, so let's try pi over 2. So x is going to be 4 cosine pi over 2, so that's going to be 0. And y is going to be 4 sine of pi over 2, which would end up being 4. So basically, in between, we went here, which tells us, so I'm going this direction, right? Because I need to get to this point, and then I need to get over to this point, and then I need to get back to where I started. So the direction we're moving is this direction. Right, so that's how our particle is going around. Questions? Sure. So basically, I know that when here I am at t equals 0, I ended up at this point. Shouldn't the y value be, oh, yeah. I see what you guys are telling me. Yeah, this should be a 5, and that should be a 5. This should be 5 sine. This should be 5 sine. And this should be a 5. Yeah. So when t equals 0, I was here at this point. If I do them kind of in order, if t is equal to pi over 2, then I'm here. If t equals pi, then that's when I was out here. So you can see that basically the way I'm traveling is I started at this point and I'm traveling around the circle in this direction. Does that help, David?
I just don't understand how you label that as like the pi over 2 and then the pi.
So they came from here, right? So like here's pi over 2. I know that this gives me the point 0, 5.
Okay, I got it.
Because x is 0 and the y is 5.
Yeah, that makes sense.
No problem. Other questions? No? Okay. So, what we really care about from this section, or going forward, is we really actually want to be able to take a derivative of a parametric equation, or a set of parametric equations, right? So we have this, we know how to take the derivative of equations when it's just x and y, and we need the derivative of our parametric equation to match the derivative of when we don't have the t in our problem. So, does anybody need me to wait before I go to the next page? Okay, so the parametric formula for a derivative is that if you're trying to find dy dx, it is the same as finding dy dt divided by dx dt. So if I have a parametric equation, I can find the derivative by taking the first derivative of, or by taking the derivative of y with respect to t and dividing by the derivative of x with respect to t. So I can do both of those. So for example, and I should say in the same manner, if you were trying to find the second derivative, so d squared y divided by dx squared, that's going to be dy dt prime. So take the derivative of dy dt and divide it again by dx dt. Okay, so it's like you're taking the second derivative of dy dt, and then you're dividing it again by dx dt. So for example, find dy dt and d squared y dt dx, whoops, this should have been dy dx. For x equals t minus 3 and y is equal to t over t minus 3. So to be able to find dy dt, to keep saying the wrong thing, to be able to find dy dx, we are going to need dy dt divided by dx dt. So I'm going to come over here on the side and find dy dt, especially because I'm going to need to use it more than once. So what are you going to use to find dy dt? Here's your y equation, right? Y equals this stuff in terms of t. How would I take the derivative of that? Yeah, I'd need to use the quotient rule. So the quotient rule says the bottom, t minus 3, times the derivative of the top, minus the top, times the derivative of the bottom, all over the bottom squared. So in this case, we're going to have t minus 3 minus t divided by t minus 3 squared. And so my t's would cancel out. So we just end up with negative 3 over t minus 3 squared. Questions? No? Okay, so this is going to be negative 3 divided by t minus 3 squared. And then we're going to divide that by dx dt. So what is dx dt? Yeah, in our case, dx dt is just 1. So our first derivative just turns out to be negative 3 over t minus 3 squared. Right? So I have the derivative dy dx, but in terms of t, which is pretty nice. If I want to find the second derivative, so d squared y over dx squared. So remember, that's going to be dy dt prime divided by dx dt. So dy dt prime, if I take the derivative of that, dy dt prime. So this we could have thought of it as negative 3 times t minus 3 to the negative 2. So the negative 2 would come down. We'd end up with 6 t minus 3 to the negative 3. times the derivative of the stuff inside, which in this case is just 1. So this is really 6 over t minus 3 cubed. So this is going to be 6 over t minus 3 cubed. Again, divided by the derivative of x with respect to t. And so the derivative of x with respect to t is still just 1. So this is going to be 6 over t minus 3 cubed. Questions? So it's a little tedious, but it's not too terrible. Okay, we're going to do another example here. Does anybody need me to wait before I go to the next page?
So I'm more confused with the nomenclature.
Okay.
So when we do the dx over dt, we're just taking the derivative of the x equals t minus 3.
Mm-hmm.
Okay, cool. I just never seen the dy's and the dx's before. I think I use a little bit of a different one in Calc 1, so I was just a little confused on that. Thank you.
No problem. Yeah, this is the Leibniz notation for taking a derivative, right? So a lot of times in Calc 1 you use y prime. But when you do implicit differentiation, usually you use the Leibniz notation because you're explicitly saying take the derivative of this with respect to this variable. And I will tell you too that as you go on into Calc 3, you use this notation more because in Calc 3, you're taking the derivatives of stuff where there's more than just 2 variables, right? So Calc 1 and Calc 2, we mostly just deal with 2 variables. But once you enter into the realm of 3 variables, you tend to see more of this notation being used. Other questions? No problem. Okay, so let's try one more example here. Okay, so find the equation of the tangent line to x equals 4 cosine t, y equals 5 sine t. So this is that ellipse we had before. At t equals pi over 4, right? So I'll come back here in a second, but we're talking about, right? So we want to know on this, was this curve here, we want to know when t is pi over 4, what is the equation of the tangent line? And in terms of, if you're thinking of this as a particle, the idea would be if your particle were to escape your loop here at some point, right, it would shoot off at the same along the tangent line, right? So in, at any given second, the particle is technically moving along the tangent line. Okay, so go back to Calc 1. You want to find the equation of a tangent line, the equation even before Calc 1. You want to find the equation of the line. What do you need to find the equation of the line? Yep, you need a point, and you need slope. So from this, we have to figure out a point, and we have to figure out a slope. So if I want to figure out the point, what am I going to do to find the point here? Yeah, plug in pi over 4 for t. Okay, so to get my point, we're going to have x is equal to 4 cosine of pi over 4. Y is equal to, 5 sine of pi over 4. So 4 cosine of pi over 4 is going to be 4 root 2 over 2. So this is going to be 2 root 2. And sine of pi over 4 is also root 2 over 2. Well, I just really want that to be a 4. So this is going to be 5 root 2 over 2. So this is going to just be 5 root 2 over 2, right? I can't simplify that at all. Okay, so my point is 2 root 2, comma, 5 root 2 over 2. Okay, so I got the point. Now I need to find the slope. So how am I going to find slope? Now that we're in calculus, right? How do we find slope in calculus? Yeah. So remember, the derivative gives the slope of the tangent line at any given point, right? So we need to find dy dx, and we need to evaluate it when t is equal to pi over 4. Okay, so dy dx, right? So it's going to be the derivative of y with respect to t. So, if I were to write it down, we're doing dy dt divided by dx dt, and then we're still going to evaluate it when t equals pi over 4. So what is dy dt? What's the derivative of 5 sine t? Yeah, 5 cosine t. All right, what's the derivative of dx dt? Yeah, negative 4 sine t. And I want to evaluate that when t is equal to pi over 4. So we're talking about 5 cosine pi over 4 divided by minus 4 cosine of pi, oops, not cosine.
Excuse me, Dr. Gorman.
Sure.
Isn't it 5 sine?
So remember, you're taking the derivative. So remember, these guys are backwards. So I'm taking the derivative of y, which is 5 sine t. So the derivative of 5 sine t would be, the derivative of sine is cosine. So 5 cosine t.
Makes sense.
And then on the bottom, we're taking the derivative of the x, which is 4 cosine t. Derivative of 4 cosine t would be negative, because the derivative of cosine is negative sine. So negative 4 sine t. And so then if I plug in here, right, we get 5 times root 2 over 2 divided by negative 4 times root 2 over 2. So the root 2 over 2's would cancel, and we're just left with negative 5 quarters. So I now have slope and I have a point. I don't care whether you use point slope form or slope intercept form. I tend to use point slope form. So remember, point slope form is going to be y minus the y value. So my y minus 5 root 2 over 2 equals my slope minus 5 quarters times x minus 2 root 2. And so that's good enough for me for a final answer. So there's the equation of the tangent line. Questions? Yeah, if I was gonna write it in y in intercept form, so I would do two things. This minus 5 root 2 over 2 is going to go to the other side. And I also need to distribute the minus 5 quarters. So if I distributed the minus 5 quarters, I'd have minus 5 quarters x minus 5 quarters times minus 2 root 2. And then that minus 5 root 2 over 2 would have to come to the other side. So you'd have plus 5 root 2 over 2. So here, this would cancel, and you'd have a 2. So, oops. So you'd really have y is equal to minus 5 quarters x plus 5 root 2 over 2 plus 5 root 2 over 2. So y is equal to minus 5 quarters x plus 10 root 2's over 2, or y is equal to minus 5 quarters x plus 5 root 2. You could plug in x and y and m and solve for your b values. Yep, you could definitely do that. You could plug in x, y, and m and solve for b. You should get that 5 root 2 that I just got. Questions? No. Okay. Okay, so this is section 10.1. So this is what I'm calling part 1. And so this is polar coordinates. And then we're going to look at, I have it called section 10.1 part 2. And so we might start that today. And then we'll go from there. So 10.1 part 1 should be nothing new. This should all be stuff you've seen in Math 127, but it might have been a while since you've done it. So that's why we're going to kind of do that. So remember, when we're talking about polar coordinates, right? So if I have a point, we're used to this point being an x comma y, right? But the idea is that our points, there's other ways we can think of this point. And so one of the other ways that we can think about this point is we can think of it as if I went out a distance r and I rotated up to get to that point. So I have like a rigid stick, right? Kind of like my pencil here. And the end is where kind of my point is going to end up being here. And what I did was I started with my rigid stick out this way, and then I rotated it a certain direction to get to my point to where it wants to be. So we rotated some angle we called theta. So we have the point x comma y, and that's going to be the same as the polar point r comma theta. So these two, so when I put the equal sign here, I mean they represent the same point. So, for example, if we think about the point 1, 1, right? The point 1, 1, so if I think about trying to make this out here, right? The easiest way to kind of think about doing this is you have a triangle here. This side is 1, this side is 1, which means this side is root 2. And if you have a 1, 1, root 2 triangle, what is this angle inside here? Okay, so it's 45 degrees, but we're going to do everything in terms of radians, right? So this is pi over 4. So the point 1, 1 is the same as the point root 2 comma pi over 2. Whoops, not pi over 2, pi over 4. Are we okay with that? Yes? No? Questions? All right. No one's typing any questions, so I'm going to assume you're okay with it. No one's also saying yes or no, so unless I'm just frozen, but I don't think so. Right? Yes. Okay, somebody typed yes. Yay. Okay. All right, good. So, okay. I was beginning to wonder because I wasn't getting any reactions out of anyone. All right, so the thing about Cartesian points, right, by saying 1, 1, 1, 1, that's the only way to write that point in the Cartesian plane, right? It is 1, 1, no matter how you look at it. Polar points, you actually can write the same point lots of different ways, right? So just like I could think of going out a distance square root of 2, and I could rotate all the way around first. So go 2 pi, and then go another pi over 4. So this also would be the same as root 2, comma, 9 pi over 4, right? Because I went all the way around 2 pi. So 2 pi is the same as 8 pi over 4, and then I went another pi over 4. I also could think of it as going backwards. So I could have, started here and went back this way. So I could have also written it as root 2, comma, minus 7 pi over 4. So the idea is there's lots of different ways that you can write polar points, right? So that's one of the reasons why we don't just always use polar points no matter what. So because they're not, it's not unique. There's not one unique polar point for every point you put in the plane. There's lots of different polar points that you could get. But when you get to Calc 3, writing stuff in polar coordinates, and then in Calc 3 you also learn about another type of coordinates called spherical coordinates. So spherical coordinates are like the three-dimensional analog of polar coordinates. So polar coordinates, we're still just dealing with a flat plane, but when you get to Calc 3, basically you redo all of not all. You redo the important parts of Calc 1 and Calc 2, but in three-dimensional space. And so in three-dimensional space, you have spherical coordinates and cylindrical coordinates. So you have two other types of coordinates that you can use. And the idea is that those coordinates actually make things easier. So that's why we kind of use these. And so that's why we take the time now to kind of remind ourselves about polar coordinates. So when you get to Calc 3, everything is not like brand new. So if you remember from Math from Math 127, there was a set of equations that helped us figure out what the polar coordinates were, right? So if I kind of drew that red line there to make a triangle on my generic point. Remember, this is x and this is y. So the equations that we use to kind of go back and forth. So we do have a right triangle here. So we can use that x squared plus y squared equals r squared. We also used the fact that the tangent of theta is equal to y over x. And then you can also figure out what the sine and the cosine of theta are, and you can rewrite the sine and the cosine of theta to actually get that x is equal to r cosine theta, and y is equal to r sine theta. So these were the four equations that should hopefully sound familiar, even if you didn't remember what they were, but sound familiar to from Math 127. And these are the equations we're going to use to go back and forth. So we're going to worry about converting points from rectangular to polar, or converting from polar to rectangular. And we're also going to worry about equations. Other questions? Okay, so let's do some of this converting. So, convert the following to rectangular coordinates. I don't know why I underlined it, but A, 2 comma pi, right? So remember, this is my r and this is my theta, and I'm trying to get to x and y. So going from polar to rectangular or Cartesian coordinates, that's the easy way. Remember, we just said x is equal to r cosine theta, and y is equal to r sine theta. So x is going to be equal to 2 cosine of pi, or 2 times -1, or -2. And y is going to be equal to 2 sine of pi, or 2 times 0, which is 0. So my rectangular coordinate here would be -2 comma 0. Does that make sense? Okay, so we'll do one more. So root 3 comma pi over 6. So again, x is going to be equal to r cosine theta. So root 3 cosine pi over 6. The cosine of pi over 6 is root 3 over 2, right? So I have root 3 times root 3 over 2, or that's just going to be 3/2. And then we have y is equal to r sine theta. So root 3 sine pi over 6. So root 3 times 1/2. So this is just root 3 over 2. So here my point is 3/2 root 3 over 2. We okay with that? Okay. We go back the other way. So I was going to go to another page. Does anybody need me to wait? Sure. Just let me know when you're ready. Okay. So convert the following rectangular points to polar. Yeah, they would be. Yeah, they would be similar to the ones used for vectors in physics. Yep. Because it's all kind of related to each other. So A, we have -1, 1. So I personally think it's helpful if you, like, at least, draw out where that point is. So -1, 1, is going to be up here in the third quadrant, right? And so remember, we need to find r and theta. So remember, r squared is equal to x squared plus y squared. So r squared is going to be equal to negative 1 squared plus 1 squared. So r squared is going to be equal to 2. So technically r could be plus or minus. You could take a positive r, you could take a negative r. It's usually easier to work with if you take the positive r. So we're going to let r be equal to root 2. And then the other equation we're going to use to find theta is we know that the tangent of theta is equal to y over x. So in this case, the tangent of theta is equal to 1 divided by negative 1. So the tangent of theta is equal to negative 1. So now you're looking for where in quadrant, what angle in quadrant 2 has the tangent of theta equal to negative 1. What would theta be equal to? Yep, 3 pi over 4. So we end up here with the point root 2 comma 3 pi over 4. Right, so the whole goal is to find the r and the theta. Questions about how I got any of that? No. Okay. B 0 to 2, 0 comma 2. If I recall, the r value is negative. Yeah, so if the r value is negative, so generally like here, like in this problem, if I had root 2 3 pi over 4, what I'm saying is go out a distance of root 2 and then rotate around 3 pi over 4, right? If your r is negative, you would go this distance, and then you still could either rotate positive or you would go out and rotate negative. So basically the r being negative means rather than starting over here and rotating to the point, right? So either going this way to this point or going this way to this point, you would start over here and you would either go this way or you would go all the way around this long way. Does that help? So again, I think it's helpful to draw the point. So 0 comma 2, right, would be up here. So again, you can use you might be, I look at this and I can just write down what the point is, right? So for me, I'm like, oh, the radius is 2. That's very clear here in this problem. And I can say, oh, the angle is pi over 2. So to me, that's very clear to write here. You can still use the formulas. If you use the formula, right, r squared is equal to 0 squared plus 2 squared. So r squared is going to be equal to 4, which again, r is going to be 2. And then the tangent of theta is going to be y over x. So it's going to be 2 over 0. So remember, 2 over 0 is undefined. And that makes sense because the tangent at this point here, right, would definitely be undefined. At this angle here, that angle is pi over 2. So when is the tangent undefined? In that first quadrant at pi over 2. So this is going to be the point 2 comma pi over 2. Questions? No? Does anyone want me to wait before I change the page? Okay. So, for example, convert the following rectangular equations to polar equations. So A, x squared plus xy plus y squared equals 1. So going from, in terms of an equation, going from rectangular to polar is the easier one. So again, we're basically going to be using the facts. If I have an x squared plus a y squared, that's going to end up being just r squared. Remember, x is going to be equal to r cosine theta, and y is going to be equal to r sine theta. So if I use those here, right, you'll notice I have an x squared plus a y squared. So together, those two are going to give me r squared. So I'm going to have r squared plus x is r sine or r cosine theta, and y is r sine theta equals 1. And you could leave your answer like that. We could, multiply out here, right? So we would have r squared plus r squared cosine theta sine theta equals 1. And if you wanted to be real fancy, you could factor out the r squared. So you'd have r squared times 1 plus cosine theta sine theta equals 1. B, I have x minus 5 quantity squared plus y squared equals 25. So again, it might be helpful to do a little bit of the algebra work first, right? So x minus 5 squared is really x squared minus 10x plus 25 plus y squared equals 25. So if I move the 25 to the other side, right, they would go away. And really I have x squared plus y squared minus 10x equals 0, right? So all I did was subtract 25 from both sides, and then I kind of rewrote the order of the terms on the left-hand side there. And then x squared plus y squared, that's just r squared. So r squared minus 10 r cosine theta equals 0. And you could factor out an r, right? So in this case, we'd have r times r minus 10 cosine theta equals 0. And you could split this, excuse me, into two equations, right? Either r is equal to 0 or r minus 10 cosine theta equals 0. R equals 0 is saying you don't have a radius, you didn't go any distance. So r equals 0 is just a point at the origin. And this other one you could solve for r. So just like we tend to like to try to solve our equations for y, if we can, we like to try to solve our polar equations for r. If we can, right? So like in my example up above, you really couldn't, but in this example, you happen to be able to. Questions? No? Okay. So let's go the other way. So, convert the polar equations to Cartesian equations. right? And remember, I think I already said this a couple times, but Cartesian equations, rectangular equations, right? We kind of use Cartesian and rectangular interchangeably. It means the same thing. So the first one here is r sine theta equals -1. So in this case, you're looking for, remember, our sine thetas are going to be y's, and our cosine thetas are going to be x's. So we're kind of basically looking for things that we can turn into x's and y's. So this one is pretty straightforward, right? R sine theta, that's just y. So this is just equal to y equals -1. So it's just a straight line, horizontal line, y equals -1. B, r equals 4 sine theta. So unlike part A, where part A was just, I could straight up use the fact that, you know, y is r sine theta, here I don't have r sine theta. I have 4 sine theta, and I have an r in my problem, so you know that 4 is not the same necessarily as r. 4 is different. It's just a number that is showing up in my problem. And so sometimes you have to get a little creative. So I really need an r next to my sine theta to be able to replace it with y. So what I'm actually going to do is I am going to multiply the left and the right hand side here by r. So we're going to have r times r equals r times 4 sine theta. So really we have r squared equals 4r sine theta. Right, so I didn't change my problem at all. I just multiplied both sides of my equation by the same thing, and I'm allowed to do that. And then remember, r squared is x squared plus y squared. So I have x squared plus y squared equals 4 r sine theta is y. So x squared plus y squared equals 4y. Questions? Yeah, it's neat. It's a different way of writing stuff, and that's kind of part of the point, right? And like I said, if you're going to go on to Calc 3, you're going to see that at times, even though, you know, if you look here, you have r sine theta equals -1, you might go, gee, that's more confusing than y equals -1, but it might be in the problem you're doing. It might actually be easier to think of it this way, just based on the other information in the problem than this way. So that's kind of why we do this. Questions? Okay, so the remainder of the stuff from section 10.1, so the stuff we're going to do today and the stuff we're going to keep doing next class, is about graphing in polar coordinates. So graphing, graphing polar equations. So graph A, r equals 2. So the first couple we're going to, I can definitely go back a second. Let me know when you're ready for me to go forward. No problem. Okay. So the first couple things we're going to graph, these would have been ones that you would have graphed in Math 127. So remember, if r is equal to 2, we're just saying that the radius is always 2. I'm not telling you anything about the angle, right? So what that is really saying is that I have a circle where the radius is 2. Right? Should put that in here. You could get it from the equation, right? So if you did this, you would have r, you could square both sides of this. So if r is equal to 2, r squared is going to be equal to 2 squared, or x squared plus y squared is going to be equal to 4, right? Remember, that's the equation of a circle. So anytime actually you have r just equal to a number, it's always going to be a circle, right? So r equals some number is always going to be a circle of that radius, whatever that radius is. B, if you think about just theta equals a number, so say theta equals pi over 3, we're saying that r can be anything we want. So if we think about going out a distance of pi over 3, whoops, and that's not the best looking pi over 3 here. Right, so I'm saying you're going in this direction, pi over 3, right? So you rotated pi over 3. And then your radius could be positive, extending out the way I have it drawn there. Your radius could also be negative and go the other direction. So anytime that you have theta equals to an angle, all that is a straight line. And again, you can get that mathematically. Remember that we know the tangent of theta is equal to y over x. So in this case, the tangent of pi over 3 is equal to y over x. The tangent of pi over 3 is root 3. So root 3 is equal to y over x. So y is going to be root 3x, right? So you have a line where the slope is root 3. Questions? No? So C, you can do things like r is between two numbers. So r is anything that's between 1 and 2, right? So remember, if r is equal to 1, you would have a circle of radius 1. And if r is equal to 2, you would have a circle of radius 2. So r between 1 and 2, you're talking about this area in the middle, so you get like a donut shape. So that's kind of cool, right? So it's a nice way to just, think about if you were writing x and y equations for that donut shape, right? You would have, they'd be much, uglier. So it's not as simple as just saying, hey, you're just taking all the r values between -1 and or not -1, between 1 and 2. You could also say, well, let's let r be between 1 and 3, but let's also restrict theta. So let's let theta be between minus pi over 4 and pi over 4. So minus pi over 4 would be halfway in here, right? Or pi over 4 would be halfway in that quadrant, and minus pi over 4 would be halfway in this quadrant. And so we're talking about the part of our donut that starts between 1 and 3. So we're talking about this fan-shaped. And then you can even get a little creative, right? Like I have here, r equals the secant of theta. So right off the bat, I don't know what that is, but remember secant is 1 over cosine. So this is going to say r is equal to 1 over the cosine of theta. And I can multiply the cosine up. So r cosine theta equals 1. And then remember, our cosine theta is really just x. So this is saying x is equal to 1. So in our secant theta is really just the straight line through 1. Right, so it's not, so it's pretty straightforward, right? Does that make sense to people? Okay, questions? No. Okay, so that's the end of 10.1 part 1, or part A, however, I think I labeled it. Let's see, what did I label? I think I labeled it part 1. Okay, so that's 10.1 part 1. What we are going to do for the rest of this is we are going to look at 10.1. We're going to start at 10.1 part 2. I think the stuff in 10.1 part 2 is really cool. It is graphing things kind of called polar roses and cardioids, and they're cool things. They're cool things to look at. No one really graphs them by hand anymore. And so you could go on Desmos. You could put these in your graphing calculator. Your graphing calculator has a polar mode to it. So you could switch to polar mode and it'll graph these polar roses and stuff for you to see. So it's not something that you necessarily have to be able to graph by hand. But I think knowing how to graph it by hand is actually helpful. So that's why I do it. And I think it's cool. It's kind of like cute, and there's some dorky math in it, in a couple places. So this is 10.1 part 2. Okay. And so we're still going to graph. We're going to be graphing things. So we're going to graph. The first thing we're going to graph here is r equals the sine of 4 theta. Okay, you might go, well, Dr. Gorman, we graph things like that in pre-calc 2. So I don't know why this is any different. So in pre-calculus, we graph things where our coordinate system, right, where we were doing like x's and y's. We graph things like y equals the sine of 2x, right? And so if you graphed y equals the sine of 2x, right, here's the x-axis, here's the y-axis. Does anybody remember what that 2 did? Nope, doesn't start 2. Okay, so, well, all right. So, the amplitude would be if there was a number in front of this, right? So if the 2 was in front of the sign, then it would make it go 2 high and 2 low. So this is still only going to go 1 high and 1 low. This 2x changed the period. Yeah, the wavelength, right? So remember the period is 2 pi over b. So in this case, it's going to be 2 pi over 2, or pi. So one wave of my sine function now, it used to go from 0 to pi, or 0 to 2 pi, but now I'm saying it's going from 0 to pi, right? And then we would have another section of the wave to go all the way out here to 2 pi, right? So Lane said it goes faster. Yeah, it's making the wave go faster, right? You get more iterations of the wave in that section from 0 to 2 pi. Okay, and it's still going 1 high and -1 low. All right. If I were to kind of label these points, right? So remember the period is 2 pi, or the period is pi here. Halfway through my period would be here, so this would be pi over 2. And another half, this would be pi over 4. So basically, when I teach, if you had me for Pre-Calc 2, I teach there are 5 important pieces on a sine or a cosine function when you're drawing them by hand to label. And so what we're basically saying is each of these little pieces here is a pi over 4. So I have a 1 pi over 4. This is 2 pi over 4. This next place here, this would be 3 pi over 4. This next place here is pi. Remember, pi is 4 pi over 4. And I could keep doing that for the second wave too, right? If I want these 5 points, so I had 4 pi over 4. This would be 5 pi over 4. This point here would be 6 pi over 4, but 6 pi over 4 is just 3 pi over 2. This would be 7 pi over 4, and then finally 2 pi is the same as 8 pi over 4. Questions? So you might go, okay, how is this cool, right? Like you said, this was cool. This doesn't look any cooler. This looks the same as it does in Pre-Calc 1 or Pre-Calc 2. And I'm going to say, yeah, so far what we've done is the same as what we've done in Pre-Calc 2. However, the difference is in Pre-Calc 2, we were graphing y equals the sine of 2x. I want to graph r equals the sine of 4 theta. But I don't just want, it's not like I'm just saying, oh, this is r and this is theta, right? If I was just replacing y with r and x with theta, this is the graph I would have. That's not what I'm doing. I want to still graph where I want to graph r's and thetas, but on the xy plane, right? So I need to think about radiuses and angles. So the first thing to notice is we're dealing with pi over 4s, right? So the first thing I'm going to do is I am going to draw in all these pi over 4 spokes here. So we have pi over 4, and then, oh, darn it. No one told me. I drew that whole picture, and you guys let me draw y equals sine of 2x instead of y equals sine of 4x. So we're just going to change this original problem then and make this r equals the sine of 2 theta. Otherwise, we got to redraw the whole little thing there. Okay, so I'm going to label all these. These are my pi over 4s, right? So pi 1, so this is 0 or 1 pi over 4. This is pi over 2, right? This is the 3 pi over 4 spoke. This is the pi spoke. This is the 5 pi over 4 spoke. This is the 3 pi over 2 spoke. This is the 7 pi over 4 spoke. And this is the 2 pi spoke. Okay, so here's the cool thing. We're going to think of these as points. These are our polar points, right? So this first point here, it's saying you're at 0 radius, 0 degrees. So if I'm at 0 radius, 0 degrees, I'm right here in the middle, right? 0 degrees, I haven't moved at all. 0 radius, I haven't moved at all. This next point is at a radius of 1, and it's pi over 4. So I go out a radius of 1, and I swing pi over 4. So that would look, I'm making it exaggerated here, but here's my radius of 1, and I've gone that angle pi over 4, right? So that's where that blue dot would be. Are we okay with how I made the red dot and the blue dot on my graph, on this like bigger graph? Yes? No? Maybe? Okay. Here's the thing. We're drawing a curve that starts from the red graph and goes to the blue graph. And what it actually does is it goes out a little bit. So it goes out and then comes back into the blue graph. So our curve actually would look something like that. Okay, so all of these things that we're drawing, we're going to be curving from one dot to another dot, and then we're going to kind of keep working our way around. The next dot here is at pi over 2, but my radius, so my theta is pi over 2, but my radius, my y value in this case, is 0. So we're coming back into here, which means I come back in. So this is why these are called polar roses, because it looks like the petal of a flower, right? So they call it a rose. I'm not really they should be like more like polar daisies. They look like daisies to me, instead of roses, but mathematicians call them roses. Okay. Questions so far? No. All right, let me change color here. Grab another color. We'll go for purple. Okay, so this point here, which I guess my purple looks, on the screen it looks a different purple. Okay, so that purple point there, so I'm on the 3 pi over 4 spoke. So the 3 pi over 4 spoke is this way. But notice my radius is -1, so I need to go out in the opposite direction to get to that -1 radius. So we're talking about here. And so we're going from this green point out here. And again, this distance is also 1. All my distances out on these spokes are going to be 1. See if I pick yellow. This point here, right? I'm at pi, but I'm back at the radius of 0. So we're coming back here into the middle. So we're going to spiral back in. If I pick another color, go for pink. Here at 5 pi over 4, so I'm on the 5 pi over 4 spoke, and then I want to go out a distance of 1, so I'm going from this yellow point back out to this pink point. So we can use this turquoise for this next one here. So 3 pi over 2, but I'm back again at a radius of 0. So we're going to swing back in again. Theoretically, each of these loops is exactly the same, right? It's kind of hard to do that when you're doing it like by hand on a piece of paper, but each of the loops is exactly the same. And let's see. Try dark blue. I don't think we've done that one yet. So 7 pi over 4, which it looks the same as kind of the purple, but so at 7 pi over 4, but I'm again at -1, so I'm going to go in the opposite direction. So we're coming back out here. And then finally, we'll do this brown color. Right, 2 pi, I'm back at 0, so we come back in here. So we cycle back in. And so we have this nice little flower, right? So our flower has 4 little petals on it, and we're basically going around. It's pretty cool, right? And we're going to learn next class how to make hearts, things that kind of look like a heart shape. And so like when one of my girlfriends, girlfriends who also has a PhD in math, when she got married, I made her wine glasses, and then on the base of the wine glasses, it was me and a couple other of our math friends, We wrote down equations, like we had equations etched onto the wine glasses that represented like hearts or two rings that were interlocked. So we like got dorky like that. And so, you know, when we were in grad school and I learned, and I'm like the first Valentine's Day or maybe the second Valentine's Day with my husband, I was teaching pre-calc. I was teaching Calc 2. And I was like, oh, that's cute. Rather than put a heart on my Valentine's Day card, I put the like equation for the heart, for the cardioid. You know, put the equation and then put my name underneath it. You know, so we're pretty dorky people. He knew what it was. He's better at this than I am. I will say that this is not the way that everybody teaches graphing in Polar. But I like doing this, teaching graphing in Polar this way because it works for every single one, right? So a lot of people, like depending, like if you have friends who are taking another Calc 2 class, like their instructor might be like, oh, if equations look like this, it's a cardioid. If equations look like this, it's a polar rose and it has this many like petals. And if it looks like this, it's a rose, but it has this many petals and the petals are on this. So rather than memorize a bunch of stuff, I just always, I always graph this way first, and then I use that to help me sketch out what is happening. And so I don't remember who taught it to me this way. I guess maybe when I took Calc 2, like my teacher taught it to me this way, and so it's always stuck with me this way. But it is, everybody doesn't teach it this way, but I actually think it's more useful. It makes you think about what is going on in the problems. But we'll stop there for today. And we're going to do more of these. So I have another flower, and then I have like a heart to do, and I have another one to do. So I have like 3 more ones to graph. And then the other thing we're going to do is we are going to find, the other thing we have left to do is we're going to find like the area inside of these, right? So we talked before about area between curves, but this is a little different because you're trying to find the area within one curve. So we're going to talk about how do you find this area next class. So those are like the 2 things we have left to do. We're going to do a couple more graphs, and then we're going to find the area in some of these graphs. Questions? No?